So this practical part now will be about how to simulate GPTP with OMNeT++ and INET. Because I think most people are mostly watching, I will now just directly do the task, and then we can discuss about the outcomes of the task. And if someone wants to do the task with me, of course, that's possible. But I think it's better to not wait if that's fine for everyone. So if I don't hear any opposite voices, I will just directly go straight to task 1, which is about how we can set up GPTP in a simulation in INET. And for that, in case you have the project open, you will see the task and some description about different node types. And we already discussed it earlier. We have in INET still the master nodes and the slave nodes, which are now called time transmitter and time receivers, and the bridge nodes. And of course, if we now look at this network here, it's not only enough to define the node types, but for example, for a bridge node, we also need to define to which node, on which node does it listen for sync messages, and to which ports does it send sync messages. And in case you're doing the task yourself, that is what you need to do in the first task. So if we now jump to the solution of the first task, we can see that the TSN clock, I think I can even show the network side by side, so it's easier to follow what's going on. Perfect. So here we can now see the network and my configuration file on the left. And we can see that for the TSN clock, because it's supposed to be our master node, we need to specify that it behaves as a master node. And we also need to say that on Ethernet port 1, it acts like a master node. For the bridge node now, we need to define the slave port, which is, because if we look into the configuration file, the first port which we configure on the switch here, the slave port, and the next 2 ports are the master ports for our TSN devices. And because the TSN devices only act as a slave, we only need to define a slave port here. And now, if you run a simulation, as you can see here, we set an initial clock time, so the clocks are initially not in sync. We can now see the time synchronization in action. So let's start up the simulation. And here on this screen, you can now see that the clocks are not in sync. The one clock is off by 10 microseconds, the next clock is off by 20 microseconds, and one by 30 microseconds. And if we now run the simulation, we can see that it starts with GPTP delay response and request messages, which are exchanged to measure the link delay, as Maheen explained in her talk earlier. After those are exchanged, we can see the sync message is transmitted from the master clock to the switch with the follow-up message, and after that from the switch to the TSN devices. And after this synchronization is performed, we can now see that the clocks are in sync because the difference of these clocks to the master clock is now 0 seconds. If we now run the simulation to the end, we can look at the result file of the simulation and check the clock drift. So let's quickly open the result file for task 1. And here we can now see until the first sync message at 125 milliseconds, the clocks are not in sync. And afterwards, the clocks are now in sync with the master clock. But of course, that's quite an unrealistic scenario because clocks are typically also experiencing clock drift. So this is what we now do in our second task. So the second task is about clocks with a constant drift oscillator. So they are having a constant drift. And if we now go back to the simulation, we can specify the drift rate of these clocks. And the GPTP standard defines that the drift rate cannot be greater than 100 ppm. So what we do is for every clock, we select a random clock drift between -100 and 100 ppm. And if we now start the simulation, select task 2, then we can see that the clocks are drifting, but they are getting synchronized again. We can see that in our result file now, which I first need to load. So now you can see that the master clock, which is the blue line here, is also experiencing a clock drift. So it's deviating from the simulation time, but all the other clocks are getting synchronized at the first sync message and also at the second sync message. And now, because I still want to do this tutorial part a little bit interactive, maybe someone has an idea what is happening at this time point in time here and at this point in time here, and why it differs from here to here. If someone in the room has an idea, of course, you can also grab the microphone or tell it to Frank, and Frank is gonna tell it to me. Or if someone online has an idea, just start talking.
Okay. Could you please repeat the question, please?
So the question was, what is happening? Also, or we can already see at 125 milliseconds, there's a synchronization happening. And again, at 250 milliseconds, there's again a synchronization happening. But what's the difference that's happening here now? What do you think is happening here at this time? Oops, sorry.
There's some input from in the online chat, maybe? Awesome. Oh, nobody has a clue. Lucas, okay. You have to tell us what's going on.
Yes, so then I will just continue. So in clock synchronization, it's not only about synchronizing the timestamp, but it's also to adjust for the clock drift. Because if we would not do that, we would always have these spikes. So the clocks would always get out of sync again. But after two sync messages, we know how fast we can calculate how fast our clock is ticking compared to the other clock. And then we can calculate the clock rate difference and adjust for the clock drift. So from 250 milliseconds on, the clocks are now in sync for the rest of the time because we set up a constant clock drift. So takeaway here is with multiple sync messages, you can also adjust for the drift rate and not only synchronize to the timestamp you received here. But of course, actual clocks are not that easy. They are not always experiencing a constant drift, but the drift might also change. And that is what we are discussing in task 3. What happens if we have a random drift oscillator, so a clock with a changing drift rate? Again, if you want to do that yourself, you should have some information on the task here. I will already present you the solution. So what we do now is we change the drift rate of the clock every 12.5 milliseconds by some number between -1 and 1 ppm. So if we run this simulation now, and look at the result file of the last simulation, we can see if we zoom in the following behavior. So now the clock drifts are changing. Let's first only look at the blue line, which is our master clock. So here in this figure, we can now see the master clock has a changing clock drift. So at some points it's ticking a bit faster than simulation time, then it's ticking again a little bit slower. And because of that, it's not that easy to adjust the drift rate anymore, which we can now see if we look, for example, at the clock of the, let's say, of the TSN switch. So here, for example, at this point, we want to adjust the drift rate and we basically take the steepness of the slope from here to here and think the master clock is continuing to tick with the same speed, so it adjusts the tick rate. But as you can see, that doesn't work because the master clock now slows down at this point here. And that's also some kind of a problem because now we sometimes over or underestimate the drift rate. And then that's maybe also some discussion here. Why do you think this might be problematic? And maybe also how do you think this issue can be solved?
Any ideas? Yes, it's already a little bit late. Last session.
Maybe a small hint. If you, for example, think about the gate control list, which you had earlier in the scheduling part, and we now have a clock that performs a time jump to the future or to the past, what could happen in those cases?
Yep. So it messes up the schedule is basically the answer.
Right. If you would, for example, take a jumping clock and you have a gate control list, you could skip, for example, the opening time or have an opening time for one frame twice if you would directly use that for a gate control list. So having clock jumps is not really desired. And that's something for the future because that's maybe a small lookout on what we are also working in the deterministic 6G project at the moment. So we're working on an improved GPT implementation on INET, which includes clock servos. So we don't perform time jumps, but we only adjust the ticking speed of the clock to slow down or speed the clock up a little bit in order to get back into sync so we don't have time jumps anymore. But this implementation is not finished yet, so that's why we couldn't include it in the tutorial here. But you can, of course, follow our project on GitHub, and then you will get notified about the next release with the improved GPTP implementation. Are there any questions on this? Because otherwise, I think we are a little bit faster than the proposed time for this tutorial.
Yep. We have a question here. Wait a minute.
Is that smooth correction of the clock after the sync? I mean, how can we assess if it is a convenient thing to do? Because I mean, correcting at once, I get that you will miss some gates because you're correcting, so your time jumps for a moment. But after that instant, you are theoretically in perfect sync, so you are in a very good timing. But now, if you smooth the correction out, then you would be still wrong for a longer amount of time. I mean, your timing would be off for longer. So how can we be sure that smoothing out that time correction is a good idea in the big spectrum? I don't know if I was clear.
That's a good question. So the standard defines that across, I think, 100 hops, the accuracy of the time synchronization has to be, I think, I'm not entirely sure, but I think it's 1 microsecond. And our simulations show that even with a clock server that only adjusts the clock speed, we are able to keep this requirement of 1 microseconds across 100 hops. You're right that you're not in perfect sync anymore, but it fulfills the requirements of the standard and solves more problem than it increases because you're getting out of sync through clock drifts in any case. So you cannot rely on perfectly synchronized clocks with schedules anyways. Does it answer your question?
Yeah, thank you. Thank you.
Thank you. Yeah. I think it would also be interesting to see how that relates a little bit to control theory, for instance, because if it were so simple to synchronize something and to put it back onto the set point and just jumping to the new value, then basically every control system should just do that, and a PID controller or something like this wouldn't exist. Yeah, exactly. Yeah. So there might be also some implications for the stability or other things in the performance of the time synchronization if you see it as a control problem. But I'm not an expert in that. It's just an observation that many control systems are, let's say, more complex than just jumping to the latest value. Yeah. Okay. Yeah. Any more questions here in the room or online about time
yes,
sync?
I still have this small question.
Of course.
I still have the small question. I wondered how realistic is it that your clock master is also randomly drifting? Is that normally how it works in a TSN setup, even if you take like a high precision clock, or?
Well, that of course depends on the precision of your master clock, but as far as I know, the standard does not define more requirements on the master clock about the accuracy. I think I showed this 100 ppm of change to real clock. I think there's no further requirement on master clocks. But of course, in a real setup, you would aim to have a master clock that is as precise as possible. And you can, of course, do that in the simulation as well. So if I go back and you would now say, okay, my normal clocks, they can have a drift between -100 and 100 ppm. You can set it like that. But then, of course, what you could do in the simulation is you say that you adjust the drift rate of the TSN clock. TSN clock. And then you could say that this, for example, might only have a drift rate of something like this. So you can, of course, do that in a simulation as well and set different drift rates for different clocks. But as I said, as far as I know, the standard doesn't define more requirements on the master clock than on any other clock.
Okay, thank you.
Yeah, any more questions about the simulation of time synchronization? Okay, I think no more questions. Thank you, Lucas, again. So this is the last time we have seen any practical task from you. So big thanks to you.